Very welcome guests. I am Abdul Moyeen, working as a field application consultant with Mentor Graphics, a Siemens business. I, along with my friend Inayat Ali from NXP Semiconductors, welcomes you to this discussion on our paper titled Structural Analysis for RDC with Set Reset Flops. This paper tries to solve a particular problem faced by design engineers trying to clean their design for reset domain crossings. Every reset signal in a digital design which can assert asynchronously is independent of any clock is called an asynchronous reset. All flops using same asynchronous reset in a digital design corresponds to a reset domain. So if a signal generated by a flop in one reset domain is captured by a flop in another reset domain, such structures are called reset domain crossings. We will use following nomenclature going forward. In general, a flop with two resets will be called a set reset flop or an SR flop in short. A reset signal forcing the flop to binary 1 will be called as set. A reset signal forcing the flop to a binary 0 will be called a reset or RST in short. The reset having priority over another in an if-else tree will be considered a priority set or a priority reset depending upon the output of the flop. The reset having lower priority over another in an if-else tree will be considered a secondary reset or a secondary set as per the depending on the value of the flop. Here you can see is a sample code of a set reset flop, and this is the most common occurrence of a set reset flop we have seen in a design, where you can see there is a priority set in the design and a secondary reset working on a neck edge. The set is working on a pause edge, you might see. The equivalent circuit is presented along with. We will use following baseline definitions to decide an RDC is safe or not. We will also consider something called a relationship between the two resets. If one reset is driven by another reset in its combo cone and is exactly following that reset, keeping all other variables as constant, this will be called a direct relationship. Which means if one reset goes 0, another is also expected to go 0. And if one reset goes 1, this also goes 1. Inverted relationship is inverse of this. If one goes 1, the another will go 0. Then this relationship between two resets will be called as inverted relationship. A third kind of relationship can be no control, means there's no connection between two resets and both of these resets are independent of each other. Based on these relationships and our baseline definition, we have prepared a detailed table as can be referred to in the poster, through which we have tried to define an RDC is safe or not depending upon the relationship between any two resets. And this table is true for a simple, basically RDC involving simple resets or SR resets, both. Consider if there is an SR reset, considering one reset at a time. Now let's consider the case 1 out of the 4 cases we have basically analyzed in this paper. To make our task easier, we have defined a few variables, and for this case 1 we have only considered the TX flop as the set reset flop. The RX flop is considered as a normal flop. So the variables we have considered are x1, x2, x3, x4 till x10, where x1 is actually tells you if the TX priority reset is a set or reset. As you can see, 0 is for reset and 1 is for set. Similarly, x2 will tell you that it is active high or active low. x3 similarly will tell you about the secondary reset for the TX flop. And x5 and x6 are similarly values for the active high or active low and the set reset of status of the RX flop. Apart from these, there are four variables x7, x8, and x9 and x10, which tells the relationship between the priority set reset and the RX reset, and the secondary set reset with the RX reset. And all the variable basically 0 0 we have considered as a direct relationship, 0 1 as the and 1 0 as the no relationship, and 1 1 as the inverted relationship. And based on these values, we have prepared our truth table, as you can see on the right of this slide. We can then solve the truth table using a Karnaugh map, and we can get an equation of SRDC is equal to such as shown in equation 1. Now if you look carefully to this equation, what this tells you? This tells you that Rx, basically SRDC, is safe only if Rx is having a direct relationship with the priority, and Rx, or if Rx is having an inverted relationship with the secondary TX reset. And both of the above cannot be true simultaneously. Hence, primary and secondary will have an inverted relationship, which is not a practical scenario and is an example of bad design. Pointing out such cases can be considered for future work on this topic. Now, for the second case, we will consider a scenario where now the RX flop is the set reset flop and the TX flop is the normal flop. Now in this scenario also you can have the same kind of variables where there is two variables for, say, x1 and x2 for the TX flop, and x3, x4, x5, x6 for the RX flop for the active high and active low, and the set and reset function of all the 6 resets in the design. Then we have relationship variables of x7, x8, x9 and x10 as defined for case 1 also. And if we take again consider the table 2 shown earlier, we can also prepare a truth table for this case also and solve it. Solving that through Karnaugh map, we can get an equation as shown in this slide. In these slides, we have, in the interest of time, covered both the remaining scenario, case 3 and case 4. Case 3 is a scenario where we have considered both the flops, the TX and RS flop, both are the SR flops, basically set reset flops. So we now have 4 variables to define the set reset values of both the nets and the priority of both the nets, basically for both the flops, for TX flop and the RX flop. And similarly, then we have 4 variables for the relationship equations. So we can solve this SRDC very similarly depending upon the table 2 shown earlier, and we get the equation as shown on your screen. The case 4 is a more peculiar thing where we are considering a scenario where the output of an SR flop is used as a reset. So you can see that there can be various scenarios if that reset is used as a TX reset or if used as an RX reset. So for in this paper we have actually solved this equation for a scenario where the third flop is a TX flop which is feeding into a flop which is using the reset generated by an SR flop. So the variables are similarly defined as you can see in details in the poster, and we can similarly define an equation which is shown in the slide. The detailed work is there in the poster. You can refer to the poster for detailed work over here. And finally, we have got these 4 equations, and these cover most common scenarios involving set reset flops, where the output is used as data, or output of an SR flop is used as reset, or SR flop is consuming some data. All the basic scenarios are covered. For generic cases, we can derive equations honoring all variables, which were around 12 variables in one equations at a point of time, the highest number of variables we used. So we can actually solve the large equation and actually get a generic mathematical equation also for an SRDC to be safe or not. Right. So this can be kept for the future work. Thank you, ladies and gentlemen. That's all.